Alright, welcome to lecture 10. This is the last lecture, which we're going to talk about kinematics, and we're going to move on to dynamics. Specifically, we're going to start talking about forces. We're not quite there yet. So let's spend a little bit of time solving some more problems that all have some things slightly unusual, perhaps, or just some new things to be aware of, to think about. So I'm going to solve 4 problems in total. Although I'm going to split this into 2 parts. In part 1 I'm going to do 2 easy problems. Then in part 2 I'm going to do 2, oops, that is a mistake. I'm going to do 2 fun problems. There are 2 levels of difficulty in physics. There's easy and there is fun. Alright, let's get started. Here's our first problem. And those problems were taken from a textbook or slightly adapted from problems you find in a textbook. A spaceship near planet Zeta is located at position R, 600I minus 400J plus 200K times 10 to the 3 kilometers relative to the planet, and traveling at V equals 9500I meters per second. It turns on its engine and accelerates with acceleration A 40I minus 20K meters per second for 35 minutes. Where does the spaceship end up when it shuts off its engine? Now, the main thing about this problem that might confuse you right now is in part, I think it's the notation. Right? It's used this IJK notation for vectors, and then of course it's the fact that it actually is a 3-dimensional problem, which we haven't had before. So far we had x and y, up and down, maybe north, south, west, east, but we haven't had motion in 3 dimensions. So we're out in space, of course, when motion in 3 dimensions is easy. So I think this problem is actually super simple once we've made sense of it, right? And making sense of it, well, that is the part that we're gonna talk about. So things we note. We note, okay, there's a mix of units. This is in kilometers. This is in meters per second. This is in meters. Oops, should have said meters per second squared. Mistake when I wrote down the problem. Meters per second squared, an acceleration. This is in minutes, but this is in seconds. So you probably want to convert everything to the same unit. We could go with meters, kilometers. Let's go with meters. I guess it's the standard, but also because these things are small numbers of meters, I guess. And I suppose we're going to work in seconds, because converting per second squared to minutes is kind of messy. I think 35 minutes in seconds, that's going to be easier. So what do we have here? We have a position, we have an initial velocity, we have an acceleration, and so we know how to handle this. All right? So all we're going to do is we're going to do what we know about accelerated motion. We just want to find the final position. So I hope you had a chance to write this down, or maybe find it in your textbook. So here's what we have. Our position R, and often we use the vector, like the symbol R, the letter R, as a vector for a general position. Not universal, but fairly common. So R is a function of time. Well, it's accelerated motion, so I know what that is. It's where you start, plus your initial velocity times time, plus 1/2 your acceleration t squared. Now, the fact that I write this down as a vector equation doesn't matter. This just stands for 3 components, like this equation with Rx, V naught x, Ax, this equation with y, initial y position, V naught y, Ay, and z, or z. So all I have to do is evaluate this component by component. So let's write down what each of those are, and then everything makes sense. So my initial position, well, let's just this R up here. It might have written it maybe like this. So I find this notation not very clear, right? It's just hard to look at. So let's convert it into a sort of vectorial form with 3 components. So it's going to be 600 minus 400. Remember, I is the x component, j is the y component, k is the z component. 200 times 10 to the 3 kilometers. Maybe I want to convert all that to meters. Well, how about I write a 6 minus 4 times 2, and 2, sorry, times 10 to the, well, 10 to the 3 kilometers is 10 to the 6 meters. Like 1,000 kilometers is 1,000,000 meters, then times 100 is 10 to the 8 meters. Again, if you're hesitating, make sure you pause the video and figure this out yourself. So this is what I'm going to use. This is my initial position. I have an initial velocity. Now the velocity, it's just in the I direction. There's no j, no k, which means that all the velocity at the time equals 0 is in the x direction. So I can write my initial velocity. So I could have written it like this, but it's the initial one. That is 9,500, 0 and 0 meters per second. I guess that's already in sensible units, so let's leave it like that. This already looks way nicer to me than this, with those funny I hats and j hats, right? Okay, I can make sense of that. Maybe even visualize this in a sort of 3D coordinate system. Of course, it's hard to draw on paper. Z, the planet sitting right here, right? So you can figure out 6 along x minus 4 along y, right? This is here. So sort of like down here, come a bit this way and then go straight up. So this is our initial position. Hard to draw on paper. Hard to draw a single point in a 3-dimensional coordinate system. There's no perspective I can apply to a single point. Okay, so I've got my velocity. What about my acceleration? My acceleration is 40I, so 40 in the x component minus 20k. Notice it's k, not j, so this is the z direction, and there's nothing in the y direction. So a, the acceleration, is equal to 40, 0, minus 20. Make sure you have the signs, right? There's a minus here, let's not forget about that. Meters per second squared. And now I just plug in. Right, so let's do this, and we evaluate it component by component. So we're going to take these, each one of them, plug them in here, and evaluate it component-wise. In fact, maybe I combine the expression first. So my r of t, right, I can write that. So I wrote it up here in vector form. I'm now gonna, so this is abstract vector notation, now I'm gonna put it into component form like I have down here. So R0 becomes, I can write like this, R0 in the, actually no, let me just continue with what we have. So this was 6 minus 4, 2 times 10 to the 8 meters, then plus 9,500, 0 meters per second times the time of the time until the end, right? Time until the engines get shut off, and then I have plus 1/2 times 40, 0 minus 20 meters per second squared times t squared. So what is t? What's the time? Oh, the time was 35 minutes. Well, that's 35 times 60 seconds. That is 2,100 seconds. That's what I want to plug in here and here. Why? Because this is in seconds, so I have to work in the same units. Now I just combine this. I combine the x component, x component, x component, y component, y component, y component, z component, z component, z component. So I can write a single vector as 6 times 10 to the 8 meters plus 9,500 meters per second times 2,100 seconds. That's this times this. Remember, if I multiply a vector by a number outside, well, it multiplies every single component. And then I have 1/2 times 40, meters per second squared, times 2,100 seconds squared. Whew. All right. And then what do we have here? This one's easy. The y is easier. This is just minus 4 times 10 to the 8 meters. 0, 0. Okay, we are done. I just write zeros here, just to make sure I notice. Okay, I've taken care of it, right? I don't see this empty gap, and I'm like, wait, did I forget something? No, it is 0. I'm just writing this down so I don't get confused later. Then the last one, 2 times 10 to the 8 meters. Plus, well, this one has 0 initial velocity, so again, this is 0. And then plus 1/2 times minus 20 meters per second squared. I've got to keep track of the minus sign. So I'm trying to write small here to squeeze it in. Could have given myself a bit more space, I suppose. Times t squared, 2,100 seconds squared. And I'm going to close my vector. Right, so this is my vector, this whole thing, where the first component is this, second component is this, third component is this, which I got from combining the first component, the second component, the third component. It's exactly what we did for just x and y, except now I have a third direction. Right, and I'm being very elaborate here, in that I spell out every step. So, but now let's just combine them. Okay, now the math, according to my calculation, says that the top becomes 708,150,000. Then this one is easy. This is just minus 400 million. And then the last one comes to, I think it's 155,900. No, 155,900,000. This is all in meters. Notice I can write the unit like inside in every component or just outside, because then it, just like a number, it multiplies every component. So this meters, this meters, this many meters. Of course, I could rewrite that as 7.08 minus 4.00 and 1.56 times 10 to the 8 meters, oops, you can't see this, or 10 to the 5 kilometers, to convert it back into the same form that I had at the beginning for a position. Right, the way it was spelled out here, or really here, but I'm not going to convert it back to IJ and K. I don't particularly like it. Other people do, that's okay. That is my final answer to the problem. That's my final position. Maybe you can visualize this in space. I've gone further along X, stuck to my Y, and gone a bit lower on the Z. It's not necessarily easy to picture this in a sort of three-dimensional coordinate system, but give it a go and see if you can do it. Okay, that was our first problem. Here's our second problem. Sand moves without slipping down a conveyor that is tilted at 15 degrees from the horizontal. The sand then falls into a pipe that's 3 meters below where the conveyor belt ends, as shown. What's the horizontal distance between the end of the conveyor and the pipe, maybe assuming the middle of the pipe, where the sand's supposed to go? Let's solve this. Now, hopefully you look at this and you recognize it is a projectile motion problem, right? Because while the sand is going from here to here, the only thing that accelerates it, in this case, is gravity, a constant acceleration downwards, no acceleration sideways. Well, that is a projectile motion problem. Now, I'm going to do something I'll be doing more and more as we advance through this course, and that is I'm not going to actually solve it for you all the way to the end. I'm just going to solve it for you symbolically, in this case, and you can plug in the values, or maybe I even stop just a little bit before the very end, and let you finish it off. Okay, so let's analyze this. Well, our starting point of the projectile motion is here. I want to compare where's this point relative to this point. So what's my initial velocity vector? Initial velocity vector in this case is downwards. And that's a bit of a subtlety here that where you might be like, wait, is this projectile motion? Yes. And the fact that you start out with a downwards velocity, so what? It's still acceleration, only in the y direction or the vertical direction, and no acceleration in the horizontal direction. So yes, it is a projectile motion problem. Just we have to be careful, as always really, about what our signs are. So this is my initial speed. Now I didn't actually indicate this. I should have noticed that that to answer this, we need the launch speed. So it's incomplete problem. Oops. This starts with some speed v0. Otherwise, we can't really answer the question. So maybe I should put here, move without slipping at speed v0 equals, I'm going to make it 2 meters per second. Squeeze this in here, and you can then plug that in at the end. Otherwise, we can't actually solve it. How do I know that? Well, I know right away, look, that if this is going super fast, it's going to end up somewhere else, and when it's going slow, even everything else is the same. So I need to know this. This was my mistake. I'm writing down the problem. I should have given the information from the beginning. Okay, so I'm assuming I'm knowing this, right? I'm aware of what this is. I want to find d. I'm going to work symbolically, so I'm going to call this angle here. I'm going to call it theta. I'm going to call this, well, this is a vertical distance, so maybe I call it the height, h, that the sand falls. Could call it whatever I like, right? But I think those are sensible quantities to use. So this one's known, this one's known, this one's known. Maybe I'll just make a note of that. This one's known, this one's known, this one's known. So this is just for me to know what quantities are given, right? And we want to find that distance d. It always helps at the start of a problem. Make sure you know exactly what you're trying to find and what's given and so on, right? I find it useful to annotate that on a diagram. Okay, so it's projectile motion. So we're probably going to define our coordinate system the usual way. I'm feeling a little bit adventurous, I suppose. So I'm going to make this my origin, but I'm going to make the downwards, my y-axis, point down today. Just for a change. Maybe in part because stuff is moving down, but, you know, just to mix it up. Nobody says I can't do that. Of course, I could also have picked my origin somewhere else, maybe this corner down here, or even that point here, somewhere altogether different. It's all fine. The motion, the x direction, we have a constant velocity, and so I know right away that the x as a function of time is going to be equal to, well, it starts at 0, it starts at the origin, so it's just going to be v0. Well, I want the horizontal component of v0. Let me just draw this again over here. This v0. This is going to be v0x. That's what I want. It's going to be v0y. And if this is theta, and this is also theta, so v0x is going to be v0 cosine theta, because it's the adjacent, and this is going to be v0 sine theta, because it's the opposite of that angle. So in our case, x of t is going to be v0 cosine theta times time. Right, we've done those kinds of problems, so it should make sense to you. This together is the initial x velocity times time. There is no acceleration to worry about here. In the y direction, we have constant acceleration. And what is that constant acceleration? Well, a in the y direction, I want to say it's minus g, right? Because it's gravity, and gravity acts down. But that would be incorrect, because my y-axis points downwards, so gravity pulls in the same direction that the y-axis points. It pulls us towards positive y. So this is a plus, right? So whether or not your acceleration due to gravity is positive or negative depends on how you define your coordinate system. In this case, I decided I wanted it to point down. I have an initial y velocity that I already figured out. That means I can right away write down my y position as a function of time. Well, it starts at 0, so there's no like initial position to worry about. That's just 0. And then we're going to have v naught sine theta times t plus 1/2 g t squared, right? Accelerated motion in the y direction. Okay. So now what we want is we want to hit the pipe. So how can I express that mathematically? Well, what I can do is I can say when the sand has fallen by 3 meters, I want it, well, what is its x position? Right? What is its position in the x direction when it has fallen 3 meters? Because that's where I'm going to put the pipe. So when it has fallen 3 meters, well, that means the sand has gone from here to down here. It is now at position plus 3 meters because it's moved in the direction of the y-axis downwards to 3. So plus 3 meters, right? If I measure what's the y position of this, I look on my ruler here, 3 meters. Had I pointed my y-axis up, we'd be going to -3, but that's not our choice. Our choice was that y points down. You could, maybe when you solve the problem again yourself, you can have y pointing up. Why not? It's a choice. Alright, so for the sand to hit the pipe, to fall into the pipe, we want, what do we want? We want that when y is equal to 3 meters, then x is equal to this distance d. So we're going to find, what d makes this true. So really what we want to find is the value of x when the sand has fallen 3 meters. Let me write this down, i.e. i.e. hopefully you notice, common abbreviation again, that is, literally it's from Latin id est, which means that is. Right? i.e. id est, that is. What was I saying? Where is the sand? You want its x position. When y is equal to 3 meters. So maybe I could have phrased it like that right away, but I phrased it like this first, and then we clarified it a bit. Right, so that's what happens. It's the thought process. I wrote it down like this. I thought maybe it could be clearer. Then x equals c. What does it mean? Oh, I want to really figure out, okay, what is the x position when the sand is at 3 meters? That's going to be my my value of d. Right? Okay. Let's work this out. Well, y equals 3 meters. So 3 meters equals y at the time when the sand reaches the pipe. Let me call it t pipe. So that's equal to, well, we have an expression for y at all times, so I'm just going to plug in the time of reaching the pipe. V naught sine theta times t pipe, because that is when we're at 3 meters, plus 1/2 g t pipe squared. Okay, so everything here is known except t pipe, so we can solve this. Oh no, it is a quadratic. And now I realize I did something rather foolish, in that I plugged in 3 meters here when I promised I was going to work symbolically all the way. So I'm just going to say, I'm going to cross this out and write h. Just whatever the height is, we know it's ultimately 3 meters. I want to work symbolically, so I'm going to correct myself here. Right, h was a given value. Yes, the value was ultimately 3 meters, but I want to work symbolically first. So wherever I put 3 meters, I'm going to put h for now. So let's write this. So this equation here then, right, h is given, 3 meters. V naught is given, theta is given, g, well, we're assuming this conveyor belt is on Earth. So we can solve this for the pipe. To do this, I realize, okay, there's a quadratic term, a linear term, and a, just a value term without any t's. So it's a quadratic. Okay, I guess I have to deal with this. Let me write it like a quadratic. G, half g t pipe squared, plus v naught sine theta t pipe minus h. Because the h went to the other side. So I can now identify my coefficients, right? This is this A, this is my B, this is my C. And so the quadratic equation then tells me that T pipe, which by now, of course, you all know off the top of your head, is 1 over G, because it's 2 times this, and 2 times a half is, goes away, times minus V naught sine theta plus or minus the square root of V naught squared sine squared theta minus, well, 4 times this, like 4ac, right? 4 times this times this. There's a minus that cancels out the minus, 2gh, like this, and that's it. Now, the x position then, oops, you can't see this, right? D, the distance of the pipe. What do you mean by D? The distance of the pipe, that is where we're going to put the pipe, well, what the x position is at the time when it reaches the pipe, otherwise we'd miss, that'd be rather annoying. So that's equal to, we had it up here, it's just V naught cosine theta times T, in this case T pipe. Now all we have to do is we have to take this part here, and we're going to plug it in there. I'm going to let you finish this off from here. But what I would do in this problem, actually, at this point here, I would be like, okay, let's plug in the values. So I get, a numerical number here, and I can just plug this in. Could write this whole expression into here. Why not? But if I'm actually just ultimately interested in a numerical value, that's what the question is asking, I'd just, work out what this is, numerically speaking, and then plug it in. Now, you're going to get 2 answers, right? Plus and minus 2 times. But what you should find is only one of them is positive. And you want a positive answer. How do we know that? You want a positive time? Well, because the sand reaches the pipe after it has fallen off the conveyor belt. It's obvious, right? It can't travel backwards in time and end up there. So why is the math giving us a second answer, right? You can tell here, if I pick the minus sign, the whole thing will be a big negative number. Well, what the math doesn't know is the math doesn't know that the motion only started here. So the math says, okay, the equations that tell me where the sand is, they describe this sort of shape and this sort of shape, right? They don't know that the pipe catches the sand here and it's all said and done. It also doesn't know that the conveyor belt starts up here. It sort of thinks what the sand did was this, like it was sort of shot up somehow, went round like this, because that's what the equations say, right? The equations that we wrote down here, nowhere does it say only applies after time equals 0. Right? We know that, but the math doesn't know it. So the math is giving us a second time, namely where the sand would have been had this motion been achieved by sort of shooting the sand upwards and watching it fly through the air and coming back in the last part of this trajectory matching what we see here. Right, so we know that this part here didn't exist. Before this, the sun was moving down a conveyor belt. But the math doesn't know this. So the math's going to give us this here as a second solution. Look, we're at the right height. If you were to plug this in, you get a negative distance too from here to here, right? Negative x position. But we know that is not the physical answer, so we know to plug in plus. But it always has some meaning. The second answer, whether it's from an arc sine, there's more than one solution, or from a quadratic equation, right? There is some meaning to it. In this case, the sort of hypothetical scenario where we've shot the sun along this arc through the air. It would have been at the same height, whatever value of time you get beforehand, before it was at that point here that we call t equals 0. So the math doesn't know, right? The math doesn't know. We only started then. Okay, you can plug in the values, you can finish it off, and that's that. All right. So those were two fairly straightforward problems. Yes, it still took a bit, but it was algebra. I was talking a lot. Hopefully you'll be able to just reproduce them yourselves. Maybe a good exercise to do right now is to stop, close the video, just look at the problem statements again and see if you can solve them again from scratch to make sure you've actually learned something watching this and haven't just gone through 2 bags of popcorn. Alright, I'll see you in part 2.